Okay, here we are doing a problem that is using or applying the intermediate value theorem. And this problem is asking us to show that the equation cosine x equals x cubed has at least one real root or one real solution. There is a real number where I plug in x for cosine x and it equals x to the third power. And we're going to use the intermediate value theorem to show this. I also am going to begin by sketching the graph of both of these functions, cosine x and y equals x cubed. And the reason I'm doing that is because it's easy, for one. So I don't want to, for the most part, do things that are difficult for myself. I mean, so difficult that it's going to take more time, and especially since it's not really part of the problem. There's no place where it says sketch the graph. But I can sketch the graph of cosine x pretty quickly because I took trig. So I did cosine x, and I can also sketch the graph of y equals x cubed pretty quickly. Now keep in mind that pi over 2 is around 3.14 divided by 2, which is around, it's around 3/2. And that we know that for y equals x cubed, which I've drawn in red there, we know that it passes through the point 1,1 because I can do simple, it's easy to see that 1 to the third power is 1. So therefore, and besides, also I want to point out maybe the x and y axis aren't to scale in this problem. All right, so I mean, as you can see, that maybe my point should be moved over a little bit, because I'm saying the pi over 2 is around 3/2, and I have 1,1 there, so that doesn't quite make sense the way I've drawn it. So it's easy to fix. Maybe I will try to fix that and say that here's 1,1 over here, and then our point of intersection then is something like that. Okay, so what I'm going to do, that's just a start to help us see that, yeah, this does make sense. And some people would say that that's a proof in itself, that I've just shown that x cubed equals cosine x for some number, and that number we're going to call c. However, we're supposed to use the intermediate value theorem, so that's just an optional piece that helps us understand what's going on. So my solution is that what I do is I take cosine x, and then I subtract x cubed and set that equal to 0. These two equations are equivalent, and then I let cosine x, I let f of x equal cosine x minus x cubed. And now I make, I'm going to put a bullet there, and then I'm going to make a statement that f is continuous because it's a difference of a trig function and a polynomial function. It's important that we at least point out that it's continuous. It's a combination, I'll just say it's a difference of a trig and polynomial function. So the thing is that I'm going to use the intermediate value theorem, and the intermediate value theorem does not apply for functions that are not continuous. Now, moreover, it's not just that I'm going to say it's continuous, which means it's continuous for all real numbers. But I also will maybe be specific and pick an interval. I'm going to pick an interval whose endpoints I can put in for x for this function f of x. And I know that there are special triangles, special angles for which I can easily evaluate cosine x. So 0, maybe you wouldn't think it's an angle, but it's a number where I can evaluate cosine 0 easily. And then another one that comes up that I think about is cosine is pi over 2, because cosine pi over 2 is 0. So just from this picture of where I have cosine x here, I can see that cosine of 0 is 1 and cosine pi over 2 is 0. And those are good numbers to put in. I've seen people putting in 1 for cosine. Well, why would I do that? I mean, I have to use a calculator, and cosine 1 is an irrational number, and it just seems like too much trouble. It is true that pi over 3 is close to 1, because pi is around 3.14. So 3.14 divided by 3, it's around 1. So if you do put in 1, it's going to be around the same thing as cosine pi over 3. But why go through that trouble? Why not use the special angles? Let's just use pi over 2. It looks nicer, it's better. Why is it better? Because it just looks better. I can't understand, why would I put in 1? Why don't I put pi over 2? F of 0 is cosine of 0 minus 0 cubed. And what I'm doing is I'm doing steps here that I think will explain the intermediate value theorem. Now notice these are the two graphs I have of cosine x and y equals x cubed, okay? But now I'm looking at the function cosine x minus x cubed. But what I see about that function is that when I plug in 0, f of 0, I get 1, all right? And if I plug in pi over 2, which just seems to me something that makes sense because cosine of pi over 2 is 0, then what do I get? I get cosine of pi over 2 is 0. Now, why am I easily saying that? Because I know this graph. I'm referring to the graph that at pi over 2, I see that cosine x intersects the x-axis. And then I subtract pi over 2 to the third power. I could simplify that or not. It really doesn't matter that much. But what I see is that I have at 0, the function's positive. And then at pi over 2, the function's negative. And it's a continuous function. So it goes from positive to negative. The function goes from positive to negative. It's continuous. Therefore, without really using brilliant thought, it's clear that it goes from positive to negative and it's continuous, that at some place between 0 and pi over 2, the function has to equal 0. And we don't know where it is. It's not actually something we can solve in terms of elementary functions where that number is. We can make a decimal approximation by using different methods. But we make the conclusion. So where I'm going to write, therefore, that's my means I'm making a conclusion. Therefore, there is a number. And sticking with our textbook, I'm going to use the letter C, where C is between these two 0 and pi over 2, such that f of c equals 0. It's not. It seems to me the logic is very clear if we can read what it says here. The function's positive, and then the function's negative. I only erased because I wanted more space. And I still maybe will make the same. I think that maybe I could have, in between here, done another step, but I'm not really sure whether I need that. But I could say, just point out what's pretty clearly right there, just above, that f of 0 is greater than 0, f of pi over 2 is less than 0. And so 0 is a number, it's a y value between the two endpoints. Okay, so I'm going to write then, that is, what's f? F is cosine x minus x cubed. That is that cosine c minus c to the third power equals 0. i.e. means that is, i.e. cosine c equals c cubed. So there is a root. This shows there is a root. that there is a real root. And I did something that I think is not good. I need to say why. Maybe over here. I like this, I can move things around. I need to write by the intermediate value theorem. What we're using here is the intermediate value theorem. The intermediate value theorem it's a little more general than the way I'm using it here. But I could say that the implication of the intermediate value theorem is that if I have a continuous function and continuous on a closed interval, that means an interval that includes its endpoints, and if at one endpoint the function is positive and the other endpoint the function is negative, then somewhere in between, there is a number between those two endpoints, between 0 and pi over 2, such that the function has to equal 0. The function's positive, then the function's negative, the y value. The y value is positive, the y value is negative. Somewhere in between, the y value has to equal 0. That's the intermediate value theorem, or it's the implication of the intermediate value theorem. The intermediate value theorem is a little more general, but that's essentially what it's saying. Okay, so I don't know if I chose the right color to do this whole thing, the blue against the this parchment color here, but I believe that's it. I'll put a little square to indicate that I finished this proof, because that's what it was. My solution was a proof. What's that? An arrow? Never knew I could do that. Okay, I'll just finish that with a little QED. Came out a little funny, but QED, done with the theorem, done with the problem, and that's all. All right, thank you. Goodbye.